In this video, we're going to look at how the gradient of f at x equals to a is related to the gradient of f inverse at x equals to b. Okay, given that f of a is equals to b. Okay, so to investigate this, let us look at the first principles of differentiation. Okay, so let's establish this relationship between the limits and the derivative of f at x equals to a. Okay, so if you recall, right, this limit will give us the gradient of f at x equals to a. Okay, so let's say that the gradient is k. Right, so in other words, f prime of a is equals to k. Okay, so let's find the limit of f inverse. Okay, at x equals to b. Okay, so this is how we can set up the limits. Okay, so notice that f inverse of b plus h is actually a plus h. Okay. So this is equivalent to this. And f inverse of b is actually a. Okay, and this will be f of a plus h minus f of a. Okay. And that gives us h over f of a plus h minus f of a, which you can see is actually equals to 1 over k. Okay, so now we have established the relationship. Let's use a few examples to test whether that's true. Okay. So I'll use e to the power of x as an example. Okay, so let's say fx is e to the power of x. And f of 2, right, is equals to e squared. Okay, so f prime x is still e to the power of x. And f prime 2 will be e to the power of 2, right? So that's the gradient of fx at x equals to 2. It's the gradient of fx at x equals to 2. Okay, so let's find the inverse, right? So we know that the inverse of fx equals to ex is actually ln x. Okay, and if you were to differentiate ln x, we're going to get 1 over x. Okay, and then at x equals to b, right? So b in this case would be e squared, right? Okay, so at x equals to e squared, the derivative of ln x will be 1 over e squared, right? So you can see that, this is k. This is equals to k. And this is 1 over k, right? Like what we established earlier on. Okay, so you can try one more examples and see for yourself whether that is true.